I'm going to throw out an observation that most of the public don't know where electricity comes from. And I don't even know that they particularly care, the broad public. They just want it available, affordable, reliable when they need it. And so education is critical to this. Policymakers, as a result of what I call largely energy ignorance, are able to do pretty much anything they want because we're not very educated as a broad public when it comes to energy. So my passion is energy education to lots of different groups, some educated and some less on energy, a lot of educated people. So that's a framework, and we'll do it in 4 quick parts. I know we have to be out of the room in a half hour, is that right? Hard stop?
3:20. I think we have a half hour.
Okay. So this is a 40-minute talk plus questions. We'll do it in a half hour. But 4 parts. Let's start kind of with fracturing. Most of you know what this is, I would guess, here. But this is a picture of a rock. This is the Barnett Shale at a very high magnification. Here's a hypothetical pore, throat or pore with methane molecules in it. If we shrink those to the same scale, and the black things are the pores, you see these little molecules, the carbon and 4 hydrogens almost go away. But not quite. You can see them up there if you're in the front. These are very small pores. Those burnt orange basketballs, I had to say burnt orange, are 20 nanometers across. So here's a human hair. We're going to shrink the pore throats onto the hair at the same scale. They look like this. So they're small. This is not the world I grew up studying, or many of you that have worked in the oil and gas business perhaps didn't grow up studying that kind of pore system. We're learning it along with our students and everyone else. So the process of fracking is you drill a well down 3,000 to 10,000 feet and now take that well laterally, and in stages you're going to inject, at high pressures. See those little things wiggling? Those are frac stages. I'm going to back that up just for fun because I worked really hard to make those wiggle. Here we go. So watch them wiggle again. That's a lot of time on an airplane there. Yeah. So those are the fracs. 3 to 6 million gallons, multiple stages now, up to 50 stages on a 2-mile long wellbore in some of the liquids. And they put 80, 85, 90% water in it, of mostly fresh, although now brines from produced waters and flowbacks. Some proppant, 10% sands or artificial, and then about 1% of these other things. And some of them you wouldn't want to drink straight for sure. Okay, it's diluted in there, but it still can be 20 or 30,000 gallons of biocides and friction reducers and that kind of thing in a well with today's technology. It's starting to evolve, but it's down fairly deep in the earth unless the permitters were asleep at the wheel. And a lot of things can happen. Then we got to mine the proppant, and that takes water to mine it off outcrops, natural sands from actually around this area or synthetic things. At the drilling site itself, there's traffic and noise and dust, and land gets broken up and erosion and things that can go on. This is at any oil and gas drilling site. It's not unique to fracking, but you bring a lot of trucks in for hydraulic fracturing. Well pads themselves are producing fluids. Those ponds at the surface can leak. It's pretty rare, but on occasion they can. You can get, when you re-inject the waters and treat it and dispose it, either dispose it deep or treat it, if you inject for long enough over a geologic fault, that fault can rupture earlier than it would have. So it can cause earthquakes. Some of those have been reasonably documented now. 3 to 4 on a Richter scale, you'll feel them at the surface. That's where the earthquakes go on with hydraulic fracturing, not the frac itself. The frac itself is done down here, completion and production. You can see that where the frac is done. And most of these figures you'll see are drawn like this. In fact, this is one of the Bureau's. Unfortunately not to scale, so I'm going to put it to scale here, vertical scale. So the surface infrastructure would look about like that, and the fracking down below, and thousands of feet of rock. So those fracs aren't felt at the surface. They're about 1 to 2 on a Richter scale. It breaks rock. It's an earthquake for sure, but it's a small earthquake. And you don't crack the rock between there and the surface, so you don't leak from there to the surface, contrary to what some films would have you believe. Okay. But things can go on when you produce those fluids, as we saw earlier. Here's the Marcellus data. This is the blue at the top is the base of the freshwater aquifer, and then the chatter around that is the deepest Marcellus wells up to the shallowest, about 5,000 feet deep. That's the microseismic showing where the cracks might have gone, kind of the maximum extent of those. And if you put something to scale here like the Eiffel Tower, You can see you're about 4 or 5 Eiffel Towers in the shallowest wells away from the fresh water of rock, mostly rock and pores. Again, you're not going to crack all that. That violates some physical principles. But if you did it 1,000 feet away from it or 500, you might be able to crack into it. So that would be poor regulation. Okay. And this is, I think, what maybe the public doesn't fully understand is the things that do happen and the things that don't happen. So when you make Dilbert, you've made the big time. We're going to start fracking under our biggest competitor's headquarters. The plan is to pollute their water and generate earthquakes to destroy their campus. The project code name is Fracking Awesome. Okay, so, and Dilbert says it catchy, and it's spelled with the requisite K. So that's what Scott Adams thinks. That's what a lot of the public think. And here's the University of Texas at Austin, our sister campus. There's a well very close to it. If you look at it from an aerial view, the green oval is where that well is located. Campus said, we don't want you drilling on the campus. So they took 19 laterals off one well pad. We call them turnhorizontals, because they actually went down, turned, and then went horizontal onto the campus. That's about, you see the scale bar, that's about 4 square miles of access from one pad. That can be done. This is technology that's improving today. So in the Marcellus, you're drilling 4 to 8 wells per pad now rather than 1. Less surface infrastructure, less need for traffic in multiple places. Improvements that are going on and being made. It's not perfect. There's still things going on at the surface, but less. So, there are regulatory considerations in all this, and these are things that are coming in many places. Baseline data that gets set. Right now we've got a lot of hypothetical conclusions out there about leakage and other kinds of things. Baseline data would help that. Cement all the producing zones, not just when they go through the aquifer. Cement the casing to the aquifer for sure. On occasion, that fails and leaks. Not very common, but it does in any oil and gas well. Minimize the freshwater, use produced waters and flow back and things. Disclosure of the chemicals. It's voluntary now. Many states have made it mandatory. Texas was the second to make that mandatory 2 sessions ago. Handle the water, treat it and reuse it instead of using fresh water. So they do that in the Marcellus now, produce it and use it. It's not enough. They got to add fresh water. There's some funny stories down in Texas. I can tell when we have, depends on how much time we have. But things that can go on, I think you're seeing these come in regulatory and policy now that make more sense with hydraulic fracturing. But there's still tension, It reminds me of this picture. I will say on this picture, this is the EPA, and we're here to help you to do your jobs. Actually, this is the winner of the last photo taken contest. Here's the runner-up from that same contest. If you're going to be stupid, you better be tough. So this is, if the former was EPA, this is the industry. Hey, look what we got, hydrofracking. Well, look behind you. There's the public. And the public kind of wants to know what's going on with hydrofracking. What's it going to do? Earthquakes are going to destroy my house, going to pollute my water, burn gas and faucets, this kind of thing. What's real and what isn't. So this is the tension, and it's important that we all work together. Let's talk about resources quickly. Mike's slides are all color-coded. Green is oil, and it feeds into transportation, industrial, commercial uses. There's biomass. Coal is always going to be gray. That's the prime fuel for electricity generation still, less than it was. Natural gas is always red, and it's versatile. You can put it in power plants, directly in your homes for heating and cooling, use it in vehicles, etc. Here's geothermal. These numbers are all in quadrillion BTUs. Physicists in the room, you can read it in exajoules, are pretty close. And it's about a TCF of gas. So, and the width of the bar is proportional to the number. Here's wind and hydro and nuclear. We said nuclear in Texas for 8 years. We say nuclear now. That's bilingual. Okay, so here's solar. That's it. That's all the fuels that come into the system on the left, and they come into power gen and directly, and on the back side, we do useful work. We move things around, and we heat and cool them for the most part with energy. And you'll see 100 units coming in the US and less than half of that out because we're not very efficient. We waste a lot. But I want to focus today on oil and gas, which is plus or minus units of the 100 still that come into our system. Natural gas globally looks like this. Production has been increasing steadily. This is OECD, non-OECD. The same exact data is split out by some geopolitical regions. You can see North America in blue across the bottom, and of course Russia in light blue, and Europe. And there's kind of a kink here that goes on pre-mid-90s. It increases in slope. We're over 30 TCF a year now, or excuse me, 115 TCF a year now consumption in the world. 115 trillion cubic feet of gas. It's a tremendous amount, and that is increasing. Where's it going to come from? This shows resources against cost to extract them. Resources are not proven reserves, they're not technologically and economically producible today. It's a total pot, if you will, and it's just an estimate around the world. But to the left of the white line is everything that's been produced and consumed to date in the world. To the right are potential resources still. So it's a lot. Can you convert those to reserves? And you see about 4 times what's been produced today in so-called unconventional reservoirs: tight gas, coal bed methane, and shale gas. Let's look at the U.S. scene. It peaked in the 70s, came down, plateaued, and has been rising. You don't hear about peak gas anymore. There was a time. And reserves have done the same thing. We'll zoom in on that 1990 window forward, and it was built like this. This is conventional gas, associated with oil and not associated, conventional gas reserves that flow out of conventional reservoirs, and it's been decreasing. But if you add in tight gas, cemented sandstones, coal bed gas, and the latest player, shale, you can see the trend reverse. And so all together, those make a pretty impressive natural gas story in the U.S. 9 trillion cubic feet a year of conventional, 14 now of unconventional, for a total of 23. So more unconventional by quite a lot than conventional. And you hear people say, boy, what a revolution. In fact, here's a talk I gave 10 years ago, almost. And this is me, not just me. This is National Petroleum Council, other data folks working, but had forecast in 2015, this is 04, in the 03 study, 10, 15, and 25. So 9, 14, and 23, not too far off there. Lower actually today in conventionals, and it's still a year to go. Probably the unconventionals will be right about spot on. So it's not a revolution. I call it an anticipated evolution. I mean, people will say, we didn't see it coming. I look at them, you didn't see it coming. Somebody saw it coming, they did it, right? Independent operators have been making this happen for a decade. Very quick transition in terms of energy. But it's been happening in the United States, and it's been anticipated. A lot of shale in the country. It's the most common sedimentary rock in the world. These pink basins, the Bureau where I am, I'm actually leading a group that's studied 4 of the biggest basins for the last 3 years. Sloan Foundation money. We're looking at the reserve and production forecast economically. There are 3 energy economists on the team, engineers and geoscientists. I'm not going to dwell on it. In fact, I'm going to go through it quickly. But I do want to show you kind of the Barnett story. This mouse doesn't work. Oh, good. Here we go. So look in the lower left corner. You see the years clicking off. In the early to mid-'80s, triangles are vertical well bores. This is stuff that George Mitchell, who just passed earlier this year, was developing. As those triangles go from blue to yellows and reds, that's better production out of vertical well bores. And then when they start to become circles, that's going to be the first horizontals, and that's going to happen right about now. So here come the horizontal drilling. "50-mile scale bar across the bottom. So tip to tail, that's about the drive I just made. Okay, it's a lot. 15, 16,000 wells, and people react to this differently. Engineers say, holy crap, $4 million a spot. That's a lot. And geologists look at it and say, wow, there's a lot of heterogeneity in there. It's not just core and non-core, which is right. And folks in environmental concerns say, man, you just painted the earth. And I remind them it's not to scale. The spots aren't to scale. But boy, when you fly over there, there are a lot of spots. Divide 16,000 by the 20 off one, you'd get 800 of these instead. That'd be a real different looking scene. So we studied all of those. we created 10 tiers. I'll go very quickly through this, but this is all published out now in peer-reviewed and oil and gas journal. And we divided these 10 tiers into high and low liquids windows, and every single well in the field was studied for its decline. So we'll zoom into that window. You can see them here now, a big fault coming across. The squares or close to squares are vertical, and the rectangles are horizontal wells. Every one of those green areas is different. That's our best guess at the drainage area, what was drained from each well based on decline curves and geology. And then the white space is what's available still to drill. So we drill all that up. It's a bottom-up study. Here's the Fayetteville, much more systematic and organized. One operator followed the Barnett, learned a lot from the Barnett, etc. And what we come away with is a forecast for the future of each year, a color there of the production and the production decline, and build this out as we drill it up. We forecast out to drilled through 2030, forecast to 2050. Again, economic recovery. We have a set of Monte Carlo simulations running at a variety of parameters, not just a price deck, but a bunch of both geologic engineering and economic parameters. A pretty neat study. We forecast there'd be 3,000 wells drilled between 10 and 12. People said we're crazy at those prices. There were 3,000 wells drilled, just about. Because people retreated into the better rock area, there were still places to drill and higher liquids. So things went on that make sense, but you have to kind of think about it in the way that operators do. Where do you go as prices come and go and technology changes? Not going to last forever. If prices stay depressed forever, these plays start to hurt. Some people make some money, a lot will not make money. And as a result, the Monte Carlo simulation looks like this. Our range of, in our base case, 45 trillion cubic feet of economically recoverable reserves out of the Barnett with a range of 35 to 56 in kind of a P10, P90 case, okay? That's bigger than most people forecast. But we've showed it to EIA, operators, published, et cetera, been through heavy peer review. And it's just, we were allowed to take a 12-person team for several years and do this, and it's been kind of fun. So what does the dry gas shale look like in the U.S.? These are all the big basins. You can see the Barnett down there in the green. The Antrim was actually the first state level. It's a lot, over 10 trillion cubic feet a year now out of shale. And here's Ken Medlock. He's on our team. He's an economist at Rice. His forecast for the U.S., all the basins out to 15 T's a year in 2040, plus or minus, which is a lot. We're consuming 20 to 23 trillion cubic feet a year today. How did this was done in 2010. Let's lay down what I just showed you on top of that, what actually happened. It's actually faster than Ken forecast so far. About 20% more than was forecast out to 2014 in the United States. And each basin is, those aren't the right colors on the right thing there, but each one is behaving a little differently. Some are better, some are worse. Prices are more depressed than the deck he was using. So we'll see where it all goes. But kind of on pace. Let's look at oil. This is global oil, OECD, non-OECD. Here's OPEC, non-OPEC, and the former Soviet Union. And then geopolitically again with North America on the bottom and the Middle East in gray, the big oil producer. Now the arrows in gas were slower and increased. Quite a different story in oil up to when I was learning to drive in the early 70s. And then the first embargo, and then a much lower slope, but increased in 30 billion barrels a year now, 30 to 31 billion. Dampened in the recession and with some efficiencies. So a lower slope, but still increasing. Oh, where is it going to come from? To the left of the white line is everything produced. To the right are resources or resource equivalents for liquids. And again, shale oil and oil shales and some heavy oils, some of the unconventional reservoirs are about 2x everything produced today. And people start to realize this, that the shales are the kitchen, the source, and the conventional reservoirs are just what leaked off into good reservoir rock that can be produced. Now the drilling is going into the kitchen. It's harder to extract it, takes more wells and technology, but there's a large volume down there. Not all economic, for sure. In the U.S., annual production, oil production looks like this, and it did peak. In fact, lots of folks claimed, they claimed many times that we were going off this cliff, this peak, and in the U.S. it did happen, that 70s. Now if you stretch it out, it didn't look very dramatic. But if you come back and look at the far right end there, you see that little blip? That little blip is the Bakken in the Eagle Ford in North Dakota and Texas. Let's take a look at those. This is a Landsat of Texas. You see Houston, San Antonio, pretty big area down to the valley. Now I'm 1994, get ready, look south of San Antonio as the picture transitions to today. You didn't know we built a new city the size of Houston in Texas, did you? Those are the rig lights and flares in the Eagle Ford. It's unbelievable. And North Dakota, the Bakken's even bigger than that. We can talk about flaring over scotch, because I just don't understand it, really, why we're doing it. I mean, I know why we're doing it, but I don't understand why we're doing it. So, how was that for clarity? But the shale looks like this. So I'm showing it a 10% internal rate of return, the price per barrel from $45 to about $70 to make these things work with a decent return. Now this is Ed Morse's forecast. He's a friend out of New York. Again, in 2010, forecast you go up to almost 4 million barrels a day in shale oil. And we've got 1 million we import from Saudi. So let's lay the actual on it. This is 2010, and here come the actual data. So we're right on pace with that forecast. Again, every basin doesn't match exactly, but pretty close to on pace for that forecast. We'll see what happens. So if you take that on the same vertical and horizontal scale, it looks like this. 1.4 billion barrels a year in shale by 2022. That's a really different looking production curve in the United States than anybody who wasn't incarcerated would have forecast. Okay? I do a lot with good friends in the Association for the Study of Peak Oil, and I joke with them now they're going to have to rename this the Association for the Study of Twin Peaks Oil, because it could be coming for a while, but it might be a peak. You know, how long will it last? And we talk about different kinds of terms. Let's look at the security implications of all this. What is security? It means it's affordable. Affordability drives energy choices today. The cost is part of that. Is the price volatile? That's part of affordability. Is the infrastructure expensive? Okay, and it varies around the world. Is it available? Can you get to it? Is there access? Is it reliable? Both, is the energy produced intermittent, or is it base load? Is it safe? That's a reliability concern as well. And finally, is it environmentally sustainable? So the 4 pillars of energy security: available, affordable, reliable, and clean, or environmentally sustainable. And we talk about clean mostly in terms of atmospheric emissions today, climate change, and local air pollution, but also is dense. How much land does the infrastructure use? And wet. How much water gets used to produce these things, both to produce and then manufacture electricity, cool, etc. So environment includes land, air, and sea, if you will. And those are sometimes in tension. So energy security, there's no energy that's perfect. Nothing lines up to satisfy all of these demands. If you look at shale gas then, let's look at it. What does it do in security terms? It helps the cost. Look at the price of gas today because of that. It makes the volatility less. We've had a pretty stable natural gas price and probably will be for a while. The infrastructure is cheap relative to more expensive forms. Natural gas power plants are reasonably affordable. The access is great. You know, not in every state. There's moratoria, and certainly not globally. But we know where it is. You can get to it. And this is a stoplight, you know, the red, green, yellow. So far, pretty green in terms of shale gas. Now, is it safe? I'm going to give it a yellow there. Natural and human causes. There are things that can happen anytime you deal with oil and gas operations. Is it clean? Well, it's cleaner than coal and oil, but not as clean as other things. Is it dense? Again, it's better than having to, say, put solar panels down across the earth to generate electricity, but there's still a lot of wells that go on. So I've got a yellow. How about on the water side? I give it a red. You know, you use fresh water, you produce water, you have to handle and reuse it. There's risk, at least from the casing to aquifers, etc. So that's kind of a scorecard for shale gas in terms of energy security. I am not going to do this because I don't have time, but we can rip through it. We'll talk maybe at the film tonight. I always get asked questions about options. If you don't like fracking, what do you like? You can't not like everything, okay? And this is a very important conversation that we're not forced to deal with when we start not liking things. So coal, nuclear, and I show the pros and cons here, wind, solar, hydro, and geothermal. These are the power generation options to natural gas, and there are pros and cons to all of them. Nothing is perfect. On the shale oil side, let's score it. Well, the cost is mixed. It's more expensive than conventional oil and some other alternatives. It keeps the volatility down. You're starting to see that. Infrastructure mixed. It's expensive to refine and move oil. Access is good. Removes the intermittency challenge. Safety is the same as shale gas. It's not as clean. I give it a red. You're making a lot of emissions. SOx, NOx, CO2. Dense, mixed, again, and then same challenges with water. So not as good of a scorecard for shale oil as shale gas on a security sense. What are the options? There are less. Biofuels, putting natural gas in vehicles, making electricity and hydrogen, which I say is just 10 years away and always will be right now. Actually, I'm a big fuel cell fan, and we have stopped investing in it as much in the U.S. right now. The Bush 43 administration was pretty keen on it. This administration, not as much in terms of research. Not as many options, and so we like our oil. No source of energy is perfect. So let's look at the world. This is the energy mix for the whole world: oil, gas, and coal, and nuclear, water, and renewables. A lot of fossil fuels in that mix: oil, gas, and coal. Let's look at it by geopolitical region. North America looks just like the world, pretty much. Again, percentage terms, I'm showing numbers in million tons of oil equivalent. If you go to Europe and Russia, you might think it's different from what you hear, but they're almost a laydown. Their energy mix is very similar to North America. South America looks different. Not much coal, a lot of hydro. They have the topography and they have the rain. Africa, just the opposite, a lot of coal, not much hydro. Middle East is no surprise, oil and gas. They're starting to build some nuclear plants. How about Asia? A lot of coal. Okay, half. This isn't electricity, total energy. Now I'm going to scale these circles to the actual consumption in the world today, proportionally. Ready? Here we go. South America, Africa, the Middle East are important, but in energy terms, not much. North America, Europe, Eurasia, and Latin America, the biggest. In fact, if you look at that circle there, more people live inside that color wheel in the world than outside of it today. Say that again. About 3.6 billion people live inside that color wheel, and less than 3.5 live outside of it in the world. You can't talk about energy without looking at that part of the world, without putting your finger there and saying, what's going to happen there as we move forward? And today they get half of their energy from coal. This is a big challenge. This is one of the great challenges as we move into a different energy future that we've got to conceptually and realistically deal with. As a result of shale gas, North American gas is cheap. That's the red line. Europe and Asia, not so much. It's not a fungible physical commodity. Like oil, we don't move it around the world on tankers yet efficiently and at scale. So that spread has a lot of interesting behaviors going on. Let's talk about the politics. Well, in Russia, they're not real keen on shale gas right now. Why? They got to export conventional gas to European markets. It's cheaper for them. Mr. Putin doesn't like it. You'll get a lot of negative shale propaganda, fracking propaganda funded out of Moscow. Same in the Middle East for oil, and well, and gas too. The Rosgas Alpha is the largest LNG exporting facility in the world right there because it comes through the Straits of Hormuz, and oil. So everything energy isn't always what it seems. A lot of funding comes out of here because they want to move conventional oil. Europe is mixed. I call them confused about their position. I say that in Europe. They agree. They're trying to figure out what they want to do. They have some, but they've got real mixed signals. And then the rest of the world is pretty keen on it. Some challenges, but mostly positive on shales. And these are the shale basins sitting beneath on the map. Okay. Geologist, does shale stop at modern coastlines? Yeah. In fact, they don't. They go off under the ocean just like other geologic formations, and someday they will in fact be developed. So there's all of that still to come. So if you look in the future, same color scheme, here's North America and Europe. We've got a forecast that coal will be replaced by gas in North America. In fact, it went faster than this. Blue is coal, yellow natural gas, 50-20 in 2004, 50%, 20%. Now they're about equal, a little more coal today. Unbelievably quick change replacing coal with natural gas. As a result, our CO2 emissions, anthropogenic, have come down to 1992 levels. It's the fastest drop of any developed nation on Earth without carbon taxes or cap and trade. Natural gas replacing coal and a recession. Okay, demand dampening plus a change in fuels. How'd Europe do? Did they get this done? Did they replace coal with natural gas and nuclear? In fact, the opposite happened. Moratorium on fracking in Germany and others, moratorium on nuclear post-Fukushima. They are now taking physical delivery of North American coal, which gets trained to the coast, shipped across on barges running on diesel, trained to Germany, and burned, along with their lignite. And their CO2 emissions have gone up the last 4 years in a row. The joy of unintended consequences. You can't not like everything. If you don't like fracking in Germany and you don't like nukes, you love coal. This is an important discussion that the world needs to have. And then look at the realistic transition times to renewables. How's Asia doing on the same vertical time scale and vertical scale? North America and Europe combined equal Asia today. The gray is coal. The forecast is even more coal. We've got to see that change. Got to see gas and nuclear and renewables come in faster there. And there are thoughts about how maybe to help them accelerate that. So the future transportation mix, I'm going to go through quickly. U.S. oil did peak and drop. Here's China on the same scale, time, vertical and lateral. We put it in vehicles. This is the U.S. vehicles sold, and these are Chinese vehicles sold, cars. So was a third, now almost 2x the U.S. So you see green being gasoline and diesel, and yellow jet fuel, petroleum products. There's Asia. No surprises. And again, this is not a judgment or a criticism. There's no reason why Asia should not grow and globalize and build their economy. They have every right to do that and are going to do it. It's just a question of what that energy mix is going to look like and how do we make it secure. I'll go very quickly through these things. This is the energy mix that to the right of the white line is my forecast or description out to 2080. And that's in percentage terms, the same thing in actual units. So you see the increases because of global demand and population. If you scale the top figure as 100%, exact same data, just a different way to plot it. You see it there, and you scale the bottom figure exactly the same. You see the demand built in. So you can compare these things now. And in 1980, we had 70% oil and coal. And mine is 40% out in 2080 of oil and coal. So that's a pretty big change in a century. 200 quads of oil and coal versus 300. 70 of natural gas, nuclear, and everything else versus 450. That's a huge change in a century of infrastructure to make that happen. And that's with a lot of efficiency built into the demand curve. Okay? If you make it real simple, it looks like this. Just the fuels we built our current economy on, oil and coal, and then everything else. Energy transitions take time. And if you've seen the film or will, now you know where we got our logo. And a little inside info. So security drives. These four parameters drive the pace of change of energy in the world. Affordability is first. Sustainability is coming on, and it's part of that mix now. So we're really talking about energy, the economy, affordability, and the environment. And that's this waltz that goes on, energy, the economy, and the environment. They dance, and you can't get it. We love ternary diagrams in geology. Has to sum to 100%. You can't, if you get all on the economy, you'll leave everything else behind. Environment, on energy. And we've talked about today about countries that have gone kind of far in one direction with unintended consequences. So really that fourth E is efficiency. It helps all of the other E's. We use less energy, the economy can be helped by that, we're more efficient, and the environment certainly is. Okay. So how do we leave our corners? We sit here in government, in academia, in industry, and we often get entrenched in things that we believe because we know we're right, right? We all know we're right, and they're wrong. How do we leave those corners and actually acknowledge that I might not be completely right, and you may have something to contribute, and you have to have some compromise to do all that. We got to get out of the corners, come to what I'm going to call the radical middle, and compromise. To learn the things in the radical middle, to act where things get done. And I'm really sincerely passionate about this radical middle. Trying to encourage us all to work together, bring what we know and compromise and get something done. Get on the same horse, sorry, everything's bigger in Texas, and ride in the same direction. So what do we summarize? Oil and gas from shale are going to be a big part of the future. But the above ground challenges are just as important, maybe more, than the below ground technical ones. Security, available, affordable, reliable, and sustainable drive. Now, policies that attempt to force a change may sound good, but they're not. It's very hard to pick energy winners. Lots of examples of failures for anybody. So we surround ourselves in the tenets of security instead, and it's easier to make decisions, smarter decisions. Diverse portfolios are inevitable. The mix is healthy, in fact. And efficiency is part of that energy mix now. And finally, the transition is going to take some time. So let's get out of our corners to that radical middle where things get done. Half hour, whew, thanks. Water time. I'll try to make my answers short. Yes, sir.
It's very interesting talk. First of all, I don't want to make the smart-ass remark about the water and fracking, so I have a serious question for you. One of the big concerns is use of water. You've been producing gas hydrofracking in ground shells for 10, 15 years. Have you had a chance to examine the impact of using that water for hydrofracking and on other uses?
Yeah. Yes. And so we at the Bureau, we actually have a whole environmental division, the Bureau of Economic Geology, where I am, our state geological survey at UT. An environmental division, we have an energy division, we actually try to do what we preach, get together, and we have a Center for Energy Economics, so it's the 3 E's. The hydro group working with the energy group has looked at all the water use in Texas. And of course, ag uses the most, and industrial, but then energy is about 2%. It's a lot, because there's a lot of water used in Texas. About half of that has been for water floods. I'm not talking about industrial uses for cooling, so the extractive industry. About half of that has been for water floods, and about half now for fracking, 1%. It's about the same amount of water that we use to water golf courses in Texas, which is a lot of water. That's not meant to be trivial. It's an arid, dry state. Okay, so we use 5 to 6 million gallons per well now and do a lot of wells. The challenge, of course, is when you get down to the arid part, we don't irrigate agriculture there. We don't do industry. All the fresh water is being used for fracking. So as you get more and more sub-regional, it becomes more and more important and has an impact. That's why we are pushing very hard to drive toward using the produced and flowback water for fracking now, the old oceans that were buried in the shale, instead of using fresh water. Ironically, in Texas, the landowner owns the water. It's the law of the biggest pump. And guess what? The landowners in South Texas require the operators to also buy their fresh water for fracking. It's more money. The operators would actually like to use the produced water. There's a very interesting irony here that's going to have to be addressed head on in the legislature. And water is tricky, especially when you don't have much, about who owns it, who gets the rights to decide what happens to it. But that's coming. What we're doing is just identifying how it's being used both destructively and agriculture. Yes, it precipitates, or it evaporates and precipitates again. As long as it's not over an ocean, you can reuse it somewhere. So it's not as destructive as putting it back in the earth and mixing it with salt water. So non-trivial, big numbers, but people are trading that off against the energy that's getting produced. Best to use it, the brines.
We really only have time for one more.
What I take from your talk is that if you really are worried about climate change, there's not very much hope.
Well, the question or the comment is, if you're worried about climate change, there's not much hope. If climate change is your number one concern today, there is an energy solution available today. And we could get there in 10 years globally. Ready? Nuclear. Resources are there, zero emissions, scalable, base load, deployable. Now I say that to students and they go, nuclear? And they actually physically back up. Are you kidding me? And I say, well, what's your number one issue? Climate change. Sounds like it's not nuclear. So we have to look at real options. And I think there's a lot of hope in the mix. I think there's transitional hope with natural gas, better but not perfect. I think there's nuclear, and I think renewables with work that's going on here in storage technologies and other places. Things are starting to happen. Storage, scalable, affordable, reliable. Scalable being the big one. So I think those things can accelerate my description of the future. We can bring it closer. But it's going to take some choices. Those are going to have to be made. And people don't necessarily like making the hard choices and looking at those, what I'll call real options.